Okay, so this lesson is about optimization. And so this section of 4 points right here, that's key point 12.15, this comes straight from your textbook. So you can definitely get it and write it down from there. You can write it down from here. It's important that you kind of know this. So when we are looking at different problems, and when we're thinking about algebraic problems or when we're thinking about real world problems, we might want to find the global maximum or the global minimum. And we've already talked a lot about, just finding stationary points, finding inflection points. Those are all the kind of critical points in our graph. And we talked a little bit about what a global maximum or a global minimum might look like, but that actually is a really important concept. So if you think about maximizing profits or minimizing costs or maximizing the amount of space that you use in a box that for packing, or minimizing the amount of air left in a water bottle, you want to have, as much liquid fitting into that water bottle as possible. Any of those are some real world examples of wanting to make sure that you are either making the most of your space or losing the least amount of money. And all of those are good examples of finding the maximum value of a function or finding the minimum value of a function. And when we say that, we're talking about our global maximum, our overall maximum, or our overall minimum. And so the steps to this really come down to, first of all, finding the relationship between A and B. When we say that, the words quote unquote relationship, we're talking about a function or an equation. So we're talking about what kind of equation can we have that will relate the two things. Sometimes they'll give you that equation. Once you have that equation, you're using that first derivative to find the stationary points. As we know, a local minimum or a local maximum very well could be our, let's say that's our graph. A local minimum or a local maximum very well could be our global minimum or maximum. So like here, right here, that's a local minimum, but that is also our global minimum. So, that's something important to keep in mind. And so we definitely want to find those stationary points because those could be our global max or our global min. And then we also are going to want to classify those stationary points because we need to know, are they local maxes, are they local mins, or are they inflection points? Okay, and so you can check that, you can classify that. We learned in our previous units that we can classify that either using our second derivative concavity test or using a sign test with the first derivative. And then the last thing we have to check is our endpoints, because a global max or a global min is not always going to be one of our local maxes or local mins. It could just very well be the endpoint of a graph. So for example, let's say our graph, and actually let's do this. Let's say our graph looks like this, and let's say they restricted the graph from 0 to 20. So here we go. We have this graph right here, and it's restricted, so we don't have arrows at the end, right? We have endpoints at the end. And when we look at that, our local minimum is our global minimum, but our global maximum actually comes from the endpoint of that graph. So when we're thinking about optimization, we're really talking about checking for several things. And I'm just going to draw a graph here. And let's say this graph is restricted based on where it's drawn. So we have this graph. Okay. In this graph example, we have two local maximums, we have two local minimums, and then we have these endpoints here. So when we're checking what are our local maxes, what are our local mins, and what are our endpoints, we're going to find, after finding all of those points, that our global minimum is this endpoint here, and our global maximum is this endpoint here. But let's say we look at this other graph. Let's say our graph looks like this. Okay, and so when we look at this, we check our endpoints, we check our local maxes, we check our min, and it turns out that in this example, our global max comes from our local max. Okay, now our global minimum doesn't come from our local minimum, it comes from this endpoint over here. Okay, let's look at another example. What if we have this drawing right here? Okay, and we look at that and we say, okay, well, we're going to check our local max, our local min, and our endpoints. In this example, our global minimum's coming from this local minimum, but our local maximum isn't our global max. Our global max comes from this endpoint over here. Okay, so the key idea that I'm hoping you're realizing from looking at these different graphs is that our local minimums, our local maximums, and our endpoints is where we're going to find our global maxes or our global mins. Okay, so those global maximums and minimums are always going to come from either a local max, a local min, or an endpoint. Okay, so in this example, we have a function that represents the height in meters of a swing, and it represents the height above the ground after a certain amount of time in seconds, and they're restricting our function for the time from 0 seconds to 3 seconds. So we only know that this function models the height of the swing between 0 and 3 seconds. We don't know that after that it's really going to model that height of that swing. So we want to find the overall minimum height of the swing and the overall maximum height of the swing. So we're going to do a couple things. We already know the functions. That was step 1 from our previous slide. Step 2 is going to be to differentiate and to find our stationary points. And so when we're differentiating this here, the derivative gives us negative 1.5 cosine of t. To find stationary points, we are going to set our first derivative equal to 0. I'm going to divide both sides by negative 1.5. And we get cosine of t equals 0. And so we have to ask ourselves, well, when is cosine equal to 0? So when is x equal to 0 is the question that asks us. So thinking about our unit circle, that's at the top and at the bottom. So that's at pi over 2 and at 3 pi over 2. Now we have to check that. Are those both in our restriction? And pi over 2 I think probably is, but we can always double check. And then 3 pi over 2, I don't think that will be in our restriction. No, that gives us 4.71. So we can cross that off. And so our only stationary point in the restriction is pi over 2. So we have pi over 2 as a possible option, and then we also have our endpoints. So what we're going to do is we are going to plug in our stationary point and also plug in our 2 endpoints all into our original function, and that's going to give us the height at that time. We know that a global max or a global min is only going to happen at a stationary point or at an endpoint. So we're going to find out what the heights are at each of those points. So I'm going to plug in first pi over 2 into our original function, 2 minus 1.5 sine of pi over 2. We know sine of pi over 2 is just 1, so 2 minus 1.5 is 0.5. So the height at pi over 2 is 0.5. Then I'm going to also plug in 0 into our original function, 2 minus 1.5 times sine of 0. Sine of 0 is going to be still 0. So 2 minus 1.5 times 0. So that just gives us the height is 2 meters at time is 0. And then we're going to check h of 3. So that gives us 2 minus 1.5 sine of 3. And I need a calculator for that one. So let's see, sine of 3 times 1.5. So that gives me 0.21168. And so when I do 2 minus 0.21168, that gives us a height of 1.79 meters. Okay, so we now know the heights at each of our key points. We know the heights at our 2 endpoints and at our 1 stationary point. We know that a global maximum is only going to be able to happen at either a local max or an endpoint. And we know that a global minimum is only going to be able to happen at a local min or an endpoint. So the highest of our 3 key points has got to be our global maximum. So our highest is this, 2 meters. So our global maximum, our maximum height of the swing, is going to be 2 meters. And then we know that the minimum height of our swing is going to come from 0.5 meters, because that's the smallest of our 3 heights. And so we have now found our global max and our global min. Okay, so when we're starting this problem, we are going to start by saying, okay, it's asking about the largest possible capacity. So that's talking about volume. And then it also tells us that we know that the surface area is 450 centimeters squared. So we also need to know the formula for surface area. And so we need to figure out both. So the volume of a cylindrical can is going to be pi r squared h. And the surface area of a cylindrical can is going to be the 2 circles, so 2 of the pi r squared, plus the area of the rectangle that makes up the entire sides, which is 2 pi r times h. So that's our surface area formula. So we're going to use both of these. So we do know that the surface area is 450 centimeters squared. So I can plug that in right there. And so we have that. So it's asking us what is the largest possible capacity. So we are trying to maximize the volume. So this is the function that we need, and we need to maximize it. The only issue is we need this function to only have one other variable, and right now it has 2 other variables. So the key for us for that is going to be to use this equation and this equation to make a system of equations so that we can maximize that volume. So we're going to either solve for r or solve for h and substitute whatever we get in for this formula right here. Now looking at this, since we have r squared and r, solving for r is not going to be nearly as easy as solving for h. So I'm going to go ahead and solve for h here. So I'm going to start by subtracting 2 pi r squared. And then we're going to divide everything by 2 pi r. And then that way we just have h. So over here, this 2 and this 2 cancel, this pi and this pi cancel, this r and this r squared leave us just with 1r. And then the 450 over 2 pi r, really the only thing that's going to be able to cancel from that is the 450 divided by the 2 is going to give us 225 over pi r. So we solved for h, and now we're going to take that and plug it in for h over here. So volume equals pi r squared times, instead of h, we have 225 over pi r minus r. And so in order to make this a little bit less messy, I'm going to go ahead and say let's distribute this and do some simplifying. So that gives us 225 pi r squared over pi r minus pi r cubed. And the nice thing about that is that these pi's cancel. This r and this r squared leave us with just 1r. So that looks a lot less messy. It's a lot cleaner. All things to be very happy about. Okay, so we're trying, the hardest part is done. The hardest part is coming up with the function that we will be able to maximize. So we got our function, our volume function, in terms of the radius, and we want to find the very maximum volume. So remember, our very maximum volume is going to be at a local min, a local max, or at an endpoint. So let's think through this for a second. There's not going to be an endpoint. They didn't specify any endpoints. We do know that the radius has to be greater than 0, but other than that, we don't have any other endpoints. So really, we're just looking for a local maximum. So we're looking for a stationary point. So to find a stationary point, we're going to take that derivative and set it equal to 0. So the derivative is going to be 225 minus 3 pi r squared. And we're going to set that derivative equal to 0. And that's what's going to help us find our local maximum. So we're going to work on solving this, dividing both sides by negative 3 pi. And so when we do that, let's see, we have 225 divided by 3. And so that gives us 75 over pi. And so when we divide that by pi, let's see, 75 divided by pi gives us 23.87 equals r squared. Then we're going to take the square root of both sides. Normally we'd put plus or minus, but we're not going to have a negative radius, so we just have to worry about the positive. And when we take the square root of that, that gives us the radius of 4.886025. Now, because we only got one stationary point, we can pretty much guess that surely that point, that stationary point, is going to be a local maximum and therefore going to be a global maximum because it's asking us for the largest possible capacity. We have no endpoints, so, this has got to be it. But to do our due diligence, we should check. So I'm going to check by doing a second derivative concavity test. So the second derivative we have is going to be negative 6 pi r. And so when we plug in that 4.886 in for r, that's going to give us a negative value. And so if that's a negative, that is concave down. So that is a maximum. So we know that the maximum volume happens when the radius is 4.88. And when we go back to the question, it's asking us what is the largest capacity. So we found that the largest capacity happens when the radius is 4.88, but we want to know what is that capacity. So the only way to find that out is to go ahead and plug that 4.88 in for our volume, our original volume equation. So volume equals 225 times the radius minus pi times the radius squared. Okay, and so after you just work on plugging that in, That gave me 1,024.36 centimeters cubed. And knowing that that's not an exact answer, we do need to round that to 3 significant figures, which is a little tricky. I think the easiest way to do that is going to be to use some scientific notation. 1.02 times 10 to the 1, 2, 3 to the third is going to be the easiest way for me to get that into into 3 significant figures. So these problems, they're not easy. I'm not going to pretend that, oh, they're a breeze, but they're really important. I think you guys can see the value in what they allow us to do and how many applications this has across the disciplines and across the real world. So, it's a worthwhile struggle, I think. And I think it's really beneficial. So our strategy is come up with the equation. Sometimes that means coming up with more than one equation and using, kind of substituting as a system. So we only have 2 variables. And then taking that equation and differentiating, finding the stationary points, plugging in the stationary points and any endpoints into the original function to check for maxes and mins. And that's kind of where we go from there. Okay, so this is an algebra problem without a context. So it's asking us to find the maximum value of this function y equals xz minus z, given that x plus 3z equals 7. This is the kind of problem that can trip people up because they're not really sure where to go with this. But the first thing that you're always going to do is see if you can use this function and get this function in terms of only 2 variables. So it's a system of equations, essentially. So we're going to start with this one and solve it for z so that we can have a function only in terms of y and x. So 3z equals 7 minus x. Divide by 3. That gives us z equals 7 minus x over 3. So that way, we can take it and plug it in for z into this function. So y equals x times, instead of z, we're going to put 7 minus x over 3. And then minus z, and instead of z again, we're going to put 7 minus x over 3. So in order to find the maximum value of this function, we're going to need to check the stationary points. And we would check the endpoints, but they didn't give us any endpoints. So we're really just going to check stationary points. And so in order to check the stationary points, we are going to need to differentiate. And in order to differentiate, we're going to have to do some algebra. So we're going to make this 7x minus x squared. And it's all over 3 here. And then we have minus the 7/3. We're going to distribute that negative, so that's minus the 7/3 plus the x over 3. And that way we can go ahead and differentiate that. And that gives us 7/3 minus 2/3 x. The negative 7/3 differentiates to 0, and then the 1/3 x differentiates to 1/3. And we should definitely combine those like terms. 7/3 plus the 1/3 is 8/3. Okay, so now that we have differentiated, we are going to find the stationary points by setting that equal to 0. And we're going to solve for x, so that gives us negative 8/3 equals negative 2/3 x. I'm going to multiply both sides by 3 and knock those 3's out of there. That's nice. So that's negative 8 equals negative 2x. So x equals 4. Up here we multiplied both sides by 3. Okay, so we get x equals 4. So we need to check and see, is this even a local maximum? Because the only chance of this being a global maximum, since we don't have endpoints, is if it's a local maximum. So we can do a quick check and see by doing a second derivative test, I think would be the easiest one. So over here, I'm going to say, okay, well, our second derivative is going to be, let's see, it's going to be, let's see, the 8/3 will differentiate to 0, and the negative 2/3 x will differentiate to negative 2/3. So if our second derivative is negative, that means that it is concave down, and so that is a local maximum, and therefore since the whole second derivative is negative, that means the whole function is concave down, which means that at x equals 4 is our global maximum. So in order to find out what the maximum value is, we're really talking about what is the maximum y value. And so we are going to need to plug that in to our function over here. And so let's see, y equals 7/3 times 4 minus 4 squared over 3 minus 7/3 plus 4/3. And so we're going to simplify that. Let's see, that 7/3 times 4, that gives us 28/3 minus 16/3 minus 7/3 plus 4/3. So that gives us 12/3 minus 7/3 plus 4/3. So that gives us, let's see, 5/3 plus 4/3. So that gives us 9/3. And so that is our maximum value because we found that there's only one stationary point, and that's when x is 4. We double checked that that stationary point is a local maximum, which also means that since there's no endpoints, it must be the global maximum. And so the y value at that x equals 4 is 9/3, and that gives us our global max. Okay, so the next slide is optional. It's for those of you who are trying to go for that 6 or 7 on the IB exam. I would watch it. It's a pretty high-level question, but it's worth looking at if you are interested. So before I go on to the next slide, I want everyone to just take note that in any of these problems where it's asking you to find the global max or the global min, I'm kind of treating all of these problems as if they are show that problems or if we didn't have a graphing calculator. And so the only way we have to find the global max or the global min is to, find the stationary points and check the endpoints. But if you have a graphing calculator, it's always, always, always an option to just graph the original function, set your window to based on the domain restriction that they give you, and just visually look for the global max and global min and go from there. That is, of course, the better choice because it's a faster choice if it's a calculator question and they don't require you, to show your work or whatever. So that's always an option for any of those problems if it's a calculator problem. But if not, you have to know how to work it by hand. Okay, so in this example, we know the function that represents the volume of water in a tidal lake in millions of liters, and T is the time in days. So first it asks what is the smallest volume of the lake, so we're talking about the minimum volume. And then it says a hydroelectric plant produces an amount of electricity proportional to the rate of flow of lake water during the first 6 days. When is the plant producing maximum amount of electricity? So as you can see, this is a red problem. Part A is a really reasonable problem, and Part B is still reasonable, but it's definitely a high-level thinking question. So let's start with Part A. So it's talking about finding the minimum. And to find the minimum, we're going to start by taking our first derivative and finding our stationary points. So our first derivative is going to be negative 60 sine of t. We're going to set that equal to 0 to find our stationary points. And when we divide by negative 60 on both sides, we still get 0 equals sine of t. So that asks us, well, when is sine equal to 0? And that is going to be, let's see, that's going to be at 0 and at pi and then at 2 pi and so on. The interesting thing about this problem is that in part A, they didn't give us a restriction. And so we know that the cosine curve, which is what our function, our original function is, we know that it is a cyclical curve, right? So that same minimum is always going to be the minimum volume the whole way through. So we're just going to find out what is the volume at time is 0, and that should give us our minimum volume of the lake. And so we don't have to worry about endpoints in this problem, which is really nice. So plugging in 0 into our function says 60 times cosine of 0. Cosine of 0 is just 1. So we get 60 plus 100, so that's 160 in millions of liters. And that is the minimum volume of our tidal lake. So talking about part B is a really high level question, and it definitely, IB is not expecting everybody to get this problem. In fact, they're probably not expecting most people to get this problem. They're expecting the highest of the high to get this part, this 9B part. So this is kind of one of the questions that probably is differentiating between a 6 and a 7. So let's take a look at it. So it says a hydroelectric plant produces an amount of electricity proportional to the rate of flow of lake water. So basically it's saying the plant is producing, you know, the higher the flow of the lake water, the more electricity the plant is producing. So whatever the maximum rate of flow there is going to be producing the maximum amount of electricity. So it says during the first 6 days, when is the plant producing the most electricity? So really this is a fancy question for saying when is the lake having the highest rate of flow of water. Okay, now remember that if the question is not asking when does it have the highest volume, it's saying when does it have it the highest rate of flow. So if it's asking for the highest rate of flow, what we're really talking about is rate of change, and rate of change is the first derivative. So in this example, what we're really trying to find is what is the maximum of this new function that represents rate of flow. When I say new function, I'm really talking about that first derivative, negative 60 sine of t. So the highest electricity is going to happen when it has the highest rate of flow, and the rate of flow is really just talking about rate of change, so it's really talking about the first derivative. So we're trying to maximize that function of the first derivative. So we want to know what is the maximum value of this function, negative sine of t. So a way that we could do that is we're going to differentiate it. And so when we differentiate it, we get negative 60 cosine of t. And we're going to set that derivative of it equal to 0 to find the stationary points. And so again, divide by negative 60, divide by negative 60, cosine of t equals 0. So that gives us t equals, when is cosine equal to 0? That's pi over 2 and 3 pi over 2. Now, in this one, they did give us a restriction. It was kind of hidden, but it says during the first 6 days. So we're talking about from when t is 0 to when t is 6. So that's really our restriction. So we're going to check 4 points. We're going to check pi over 2, we're going to check 3 pi over 2, we're going to check 0, and we're going to check 6. Whichever one gives us the maximum is going to be our maximum flow of energy. So we're going to plug them into the function that represents rate of flow and see where that takes us. So negative 60 times sine of pi over 2. We know that sine of pi over 2 is 1. So that gives us negative 60 as our rate of flow. So that's losing water, right? Okay, then we're going to check 3 pi over 2. So sine of 3 pi over 2 is negative 1. So that gives us positive 60. So that's a positive rate of flow, right? Gaining water. And then we're going to check the two endpoints. So negative 60 times sine of 0. Now sine of 0 is going to be 0. So that's going to give us negative 60 times 0 is 0. So that's not it. And then we are going to check sine of 6. So we need our calculators for that. Sine of 6 times negative 60. Let's see here. And that gives us positive 16.8, rounded to 3 significant figures. So that's not it. So the maximum rate of flow is at 60, right? 60 liters per day, okay? And the question specifically says, when is the plant producing the maximum amount of flow? So our answer is not 60 because that's the maximum amount of flow of lake water. The answer of when is at 3 pi over 2. And so that is the time that it is producing the most. So our final answer is at 3 pi over 2. And we could find out how many days that really is by doing 3 times pi divided by 2. And that gives us technically after 1.57 days.